Hi, and welcome to our presentation about macOS security, escaping the sandbox and bypassing TCC. My name is Keuper, and I'm here today with my colleague Alkemade. We work for Computest. Computest is a security company in the Netherlands. We offer services like penetration testing, training, etc. And specifically, we work for the research department, Sector 7, where we conduct security research. We researched the internals of macOS security, but you might also know us from our entrance in this year's Pwn2Own competition, where we have demonstrated a zero-day attack against the Zoom video conferencing client. So, suppose the hypothetical situation that you have code execution on a macOS installation as an unprivileged user. How do you get from that starting point to having access to either root-owned files or accessing stuff like the camera and microphone, etc.? Which hurdles you then have to overcome? Those are topics we would like to discuss with you today. So for that, we divided the presentation in two parts. First, I will take you through all the current mitigation techniques that are implemented in a modern macOS installation. Secondly, my colleague Thijs will walk you through some of the vulnerabilities we have found during our research. For this, we have to note that many of the vulnerabilities we have discovered are still unfixed. So we'll give Apple some more time to fix those vulnerabilities, but as a consequence, we can discuss many of the concepts we have used, but we cannot share any very specific details about the vulnerabilities. So let's start with the security mechanisms in macOS. And I will just go by them one by one and give an explanation on how each technique works and what it implies. So the first technique we would like to talk you to about is Gatekeeper. And Gatekeeper is actually the code name for something that is well known as code signing. And it was introduced in macOS Lion, which was a long time ago. And it's currently required if users would like to install an application that it's signed by Apple. Users still have the option to also install applications that are unsigned, but they have to explicitly approve running that app in the privacy and security settings. The verification of the code signature is handled by a kernel extension, which is accompanied by a user daemon for the signature verification. An important part of code signing is what macOS calls entitlements. The same technique also applies to iOS, but every code-signed application can be given a very fine-grained set of permission by Apple, which are called the entitlements. And very specific permissions are given out to specific applications. For example, VPN application needs to make changes to the current network stack. So the VPN software will get a very specific entitlement for that. And what currently is happening is that to make the attack surface for a specific application that requires certain entitlements as small as possible is that those entitlements are only given out to small helper daemons, which will be signed and giving a specific entitlement. And the larger application will use an inter-process communication system, which on macOS is typically XPC, to actually talk to the smaller helper daemon. So having code signing is an important security mechanism in the macOS ecosystem. But it is important to realize that once an application has a specific entitlement and is signed, that signature is valid basically forever. So if you, as a malware developer, for example, you would like to have certain privileges within the macOS ecosystem, What you can do is just download an older version of some software that has a known vulnerability in it, but it does have a signature with the entitlement you would like to use. And since the signature is still valid, you could just use the vulnerability in the software, and you will have the same privilege. There is a tool which you can use to look for the entitlements of a specific application. For example, this is the output for the PS utility. And to get process information, you'll need a special entitlement called task for pid allow, which allows PS to get information about a different process. You can also look at the code signatures for each application. And basically what happens is that every static code page in a MacOS binary will have a specific code signature over that segment. The code segment is typically at the end of the binary. You can extract it, you can unpack it, etc. So another thing to realize is that the binary itself is signed and it is checked upon every execution. So if you change the binary, the next time the application will start, it will have an invalid signature. The resource sources, however, although they are also signed, they are only checked once, but only if there is a specific quarantine bit set on the application. So if you change the resources of an application after it's run the first time, the code signature will not be validated for those resources. That might pose a threat, but it is also, this is done due to the performance impact it will otherwise have on loading an application, because if there is a lot of resources, then you also have to hash the entire file to check the signature of the resource for every execution, which is very time consuming. So in a later macOS release, macOS Mojave, we have something which is called a hardened runtime. This is enforced for apps that are installed via the App Store. And basically, it protects the app from various forms of process injection. So it prohibits some environment variables to dynamically load different shared libraries, etc. So this is something that is enforced for apps that are installed from the App Store. We come back to a hardened runtime at a later point in this presentation. Next is Seatbelt, which is the app Sandbox implementation in macOS. It has been around since macOS Leopard, and it is enforced for almost all applications. So apps from the App Store will get a specific sandbox profile. And since macOS Lion, it's also the case that every application will get its separate container, which is similar to iOS, wherein the application will have its documents folder, etc. The implementation of Seatbelt is handled by the Sandbox kernel extension and a company daemon, which runs in user space. So the sandbox profiles are written in the scheme language and can be found within the file system. And the sandbox implementation has hooks in all system calls. So across the entire kernel tree, you will see calls to check if the specific system call is allowed within the current sandbox profile. And the profile is based on the entitlement of an application. As some kind of entitlements require some additional sandbox exceptions. This is an example sandbox profile. This is for the iMessage address book application, where you can see it can communicate with certain services and can read and write certain files. The next protection mechanism we would like to talk to you about is System Integrity Protection, or SIP. It was released in macOS Alkemade 10. It is sometimes referred to as rootless, and internally it's often referred to as CSR, which stands for Configurable Software Restrictions. And it is aimed at limiting the power the root user has on a system. As Apple described it, typically on a pre-Alkemade system, the attacker was only one password prompt away from getting full system access. Most systems only had one user. The user also has system privileges. So if you have access to the user account, you typically only need the password so you can escalate your privileges to root. And then you could modify any part of the system. So system integrity protection is aimed at limiting the power the root user has. It restricts file modifications. It restricts the loading of kernel and system extensions. It restricts things like process debugging, so you cannot attach a debugger to many system processes. If a specific file or directory is protected by SIP, is something you can check by requesting the extended attributes on a file or directory. For example, you can see that the entire /bin directory has an attribute of com.apple.rootless, which means that that directory is protected by system integrity protection, and the ls binary is restricted, which means you cannot read or write, or you cannot write to the binary. So basically, the technical implementation of system integrity protection is just another sandbox profile. You can look at the configuration in a modern Mac system, and SIP is enforced by a configuration variable. So that variable is placed in NVRAM. So you so at system boot, it will read that variable, it will know system integrity protection is turned on, and it will enforce it from early boot stage. You can change that variable, of course, by just resetting the NVRAM variable. However, setting the specific variable for disabling SIP is also protected by SIP. So if you would like to disable it, you can boot into a recovery mode, change the NVRAM variable, reboot, and then the system will boot without a SIP protection enabled. So another thing that is recent in modern macOS operating system is something that is called transparency, consent, and control, or TCC for short. And you have probably seen this as a macOS user when an application requires access to you or requests access to your camera or microphone. This is something that is handled by TCC. So this is done to further limit the normal access a typical application has. So a typical application can no longer directly access your camera. It first needs to ask permission before it's allowed to get the camera feed. It was introduced in Mojave, and it is basically a dynamic sandbox for privacy-sensitive subsystems. Whereas the sandbox we talked about earlier is a static sandbox. It won't change over time. TCC is dynamic, as in users can give access or also revoke access. So permissions are inherited from the parent process, and the permission an application has is stored with the bundle ID and the developer ID. So the same thing applies here as to Gatekeeper, the code signing system, namely that if an application has a specific set in permissions, you could just run an older version of the same app which has a known vulnerability, and you as an attacker will also will be able to also inherit that permission. So how this works is you have two TCC daemons running, or at minimum of two. Basically, for each user will have its own daemon running, and the daemon will have an open connection to a database file. The content of the database file is protected by system integrity protection, so you cannot write directly to that file. But how it works if as soon as an application requests access to a specific functionality, the underlying daemons will start communicating with each other to see if you already have that app already has access. For example, if you would like to record audio, that is done via the core D audio subsystem. It will send a message to the TCC daemon to see if that specific application already has access, and if not, the TCC daemon will send a message to the notification center, and that will show the pop-up to see if you want to either accept or deny the request. For this, the TCC daemon has some very specific entitlements that no other application has, namely the notification center TCC entitlement and the TCC manager entitlement, so it can also write to the database. The last thing I would like to talk to you about is the signed system volume, which is relatively new since Big Sur. The first step were introduced in a previous version of macOS with the introduction of the Apple file system, which is the new file system replacing the HFS, older file system. And in a current macOS installation, the system volume and the data volume are separated, which means that the system volume holds all macOS core files, which won't change over time, only with an OS upgrade. Those are on a different volume than all your data files, so like your documents, but also your customly installed application, etc. And this makes a very complex file tree, which Apple describes as a bidirectional wormhole in path reversal. They use a technique called firm links to basically map certain points of the data volume over the system volume, so that you get a full file tree where certain files or directories will be writable, where others are located on the system volume and they will be read-only. So the read-only system volume was introduced in macOS Catalina, and it protects the macOS file system from tampering. Only in Catalina, if you had root privileges or kernel access, you could remount the system volume as writable, and you could still make changes to the core file system. In macOS Big Sur, this has been upgraded to also add a cryptographic signature over all data on the system volume. So even if you remount the entire system volume as being read and writable, then you could still not change, or you could change the files on the system volume, but the system would no longer boot that specific version of the file system because the cryptographic signature is invalid. So this is implemented by using a Merkle tree, and that Merkle tree is validated on every boot. So the hash metadata is stored within the APFS file system, and the root node, which is called a seal, is cryptographically signed by Apple. If the seal is broken, the system will reboot from a previous snapshot. The relevant data structure are well documented within the Apple file system references if you are curious about the details. So then comes the question, okay, but then how are system updates installed? For this, macOS has a permanently hidden update volume, so you won't see it in the disk utility application. but it is there and it contains a snapshot of your Big Sur installation. And patches are applied to this specific snapshot. And if everything succeeds, the snapshot is sealed and the system is rebooted, and it will then boot from the new snapshot, which has a valid signature. But if somehow the update fails, the system will just continue booting from the previous snapshot and it can try again. This also makes the update process a little bit more robust. You can use the disk-util utility to check if your current running snapshot indeed has a seal that has been verified. So during our research on the specific details about this implementation for this presentation, we came across a reproducible kernel crash when entering some commands. So it might be that there are still some vulnerabilities there in the newly added cryptographic seal. So we might get back to you at that at a later point. So to give a short introduction about all the things we talked about, the code signing guarantees that the code was published by a specific organization and it was not altered after the fact. The seatbelt handles the static permission an app has, like read or write access to specific locations. And TCC handles user control permissions like camera access, screen recording access, etc. Those are dynamic. SIP guarantees the integrity of a system as a whole, so that you cannot change the certain key parts of the operating system. And the signed system volume prevents modification of system files and makes sure that every reboot it is in a known good state. So if you look at how important Apple considers those protection mechanisms, you can of course look at the amount of bug bounties they are willing to reward for vulnerabilities circumventing those protection mechanisms. And you can see the TCC vulnerabilities are up to $100,000, which implies that they really believe in the implementation of TCC and its effectiveness in protecting their users' data. So this was all about the internals of macOS and how it tries to protect the data from its user. I'm going to hand over the rest of the presentation to Thijs. He will talk about some of the research we have done and the vulnerabilities we have found. So Thijs, you're up.
Okay, I'm going to talk about a couple of the vulnerabilities we found as a demonstration of these security mechanisms, mainly to demonstrate how they can fail or how they can protect certain parts, but also to show that there are still some weaknesses in many of these protections, stuff that Apple hasn't really gotten right, or maybe applications haven't really picked up on. And the first one of those is privileged updaters, and that's going to be mainly Adobe Acrobat, but there's also some others that we will cover later. This is an example of where code signing is important, even in third-party applications. So not in the system itself, but in third-party applications. First of all, there are some systems there with a main user who does not have an administrator account. So it has a standard user. For example, it may be a computer that's used in school, or maybe a computer used by a child or a parent or a teacher has the administrator user, but the normal user, the day-to-day user, has a standard user account. This can create an issue because non-admin users are not allowed to change anything in the applications folder. So how can updates be installed in this case? There are many applications that try to install updates automatically without any interaction from the user. And in order to do that, the application needs to write to the applications folder, but the user itself does not have permission to do that. So there's one quite simple solution for that, which many applications have adapted in the same way. That's to use a service which is running as root to handle the installation. This is often known as a privileged helper tool. How this works is typically like this. So the application itself checks for updates and then downloads a new update package, and then it communicates with the service in order to handle the installation. But there are two checks here that are very important for the security of this process. First of all, the service should verify that the incoming connection or the incoming request really originates from the legitimate application. Otherwise, it might install something completely different. And second, the update package should be signed. Now, how this works typically depends on the type of package that is used. But one common method is to use macOS package files, which can have a signature embedded in them. If those checks pass, the installation can proceed. But if there's something wrong, then there might be privilege escalation here. So how this can often go wrong is that the first step, there might be an incorrect code signing check. Sometimes the code signing check is completely missing, or there might be a process injection vulnerability. We'll cover those later. In the second step, can also go wrong, and that's often a time of check, time of use type of vulnerability. What this means is that the service checks the package and then installs it, but in between those steps, something else changes the contents of the update package, and then it installs something different from what it checked. And if you have the combination of those two vulnerabilities, then there's the potential for privilege escalation. And even though you need two vulnerabilities here, it is very common that both of those are present in applications that use an update mechanism like this. For example, Adobe Acrobat was found to be vulnerable. This was found by Yuobin Sun of Tencent Security Xambu Lab. There was no code signing check at all, and it was possible to use a symlink for the update package. So then you could change the package in between the code signing check and the installation by pointing the symlink to a different package. He documented this vulnerability quite well. But then I and somebody else at the same time, Susawa Fitzel from Offensive Security, looked at it. Susawa was a bit earlier and reported this earlier. So he found that the code signing check was implemented incorrectly. They used a method which was quite easy to tamper with, and it was possible to use a hard link to the update package. In this case, they moved the update package to a different location, which meant that any hard links to the same file were kept intact. So by changing the hard linked file, it was possible to change it in between checking and installing. I looked at it a little bit later, but before the update was released, and I noticed that when the update was released, that my exploit still worked with a few tweaks. They implemented a correct code signing check, but it was unfinished. It always returned true. And it was possible to use an open file descriptor for the same file, for the update file, because it was still moved. So, as you may know, a file descriptor in macOS is a handle to access a file. You can read or write to it. And the permissions for the file are only checked when you open that file descriptor. So if you open a file and then you move it to a different location and you change its permissions, then you're still allowed to read to it, even though you may not be allowed to open it again due to the permissions. So I reported that to Adobe, and now I think it's finally fixed correctly and it's no longer possible to use this for privilege escalation. But maybe I'm wrong. Maybe somebody else finds a trick that can be used to bypass this again. Now, many other applications that have been found to be vulnerable in a similar way. Google Chrome had a vulnerability like this at some point. Microsoft Auto Update for Office had this type of vulnerability. Microsoft Teams had a similar vulnerability too recently. And there's another unnamed company that's still under disclosure that we cannot talk about just yet. But this is even a more bigger problem here than it may seem, because macOS users are very used to just deleting an application if they want to uninstall it. If you no longer need it, then you just drag it to the trash and then it's gone. But if you do that, then most of the time the privileged updater is still there because it was not part of the application bundle and it might still be installed. And because, as I mentioned, the application handles the checking for updates and downloading, the service by itself will not update itself. So it's very well possible that if you have used Adobe Acrobat in the past at some point, that you still have a vulnerable updater installed, even though you have deleted Adobe Acrobat. It can still be that the updater is still there. So check your launch agents or launch daemons for stuff that still can be started automatically. So therefore it's also good to make sure that if you implement something like this, that you implement a sort of self-destruct mechanism if the application is gone, that the privileged updater also uninstalls itself. Next one is about open and safe panels. And I mean this by that. So it appears to be a very boring part of the macOS UI. But from a sandboxing point of view, this is actually a very complicated piece of technology. Because the contents of the panel can see all of your files, everything you have. But the application may be sandboxed. So it's possible to see a file there, even though the application itself cannot read it. And the way this works is by using a separate service. So there is a open and safe panel service, which is drawing the contents of the panel. And then the application itself is providing the window. So if you're used to web applications, this is kind of like having an iframe within a web application where the contents are being drawn by something else. So this open and safe panel service is an XPC service, which does have access to all of your files. And then when you select the file and you click the open button, the temporary access to that file is being given to the application. So then the application can save your file or open it temporarily. So I think this is a very interesting security boundary that probably hasn't received much attention yet, but it's quite important for sandboxing. One thing I noticed was that this is all entirely a private API. There's no public part of this that you can use. And one of the important classes in this is the NSRemote_View. This is the class that is providing the drawing of the contents of the panel. This has, for macOS, for Objective-C classes, you can inspect at runtime the methods that it supports. So even though it is a private API, you can look at all of the methods it has. One thing I found was that it has a snapshot method, which, as you may expect from the name, takes a snapshot of the panel and returns it to the application. So for this way it is used, it is quite a big vulnerability, because it means that the sandboxed application, even though it doesn't have access to your files, normally it can't list your documents folder, for example, it can take a snapshot of your open panel to get a preview of files and a directory listing of a specific folder. So we have a demo video of that. So you can see here, this is the actual panel. And now the application has taken a snapshot. So this snapshot part is accessible by the application, but the other contents of that window are not. And Apple fixed this in the Big Sur release by adding another entitlement check. If you want to use a snapshot method, then you need to have a specific entitlement in order to use it. Next one is a sandbox escape we found using system preferences. One thing that's interesting about the Mac application sandbox that on iOS you cannot do is that you can use fork and exec. So, for example, you can use ls by calling system, and then it just executes, and it inherits the same sandbox as the application that uses it. So, ls here can read the root folder, but other folders it would not have access to. This was interesting that this is possible. But there's also one other thing about Sandbox, and that is that if you try to do something that is not allowed, then it usually just returns an error message or an error code, but it doesn't terminate your application. There's one exception to that, and that is trying to enforce a sandbox while you are already sandboxed. So if you try to launch Safari from a sandbox application, Safari itself being a sandboxed application, then the kernel will terminate it because it's trying to initiate a new sandbox. So as you can see, this is the message that you will get in your log if you try to execute Safari from a sandboxed application. But other applications which are not sandboxed, you can launch from a sandboxed application, and then they're suddenly running within a sandbox. We tried this with a lot of applications, and we found some interesting results. System preferences, we noticed, was working fine. Many other applications, they were hanging or they were permanently waiting for something that they were never going to complete, like disk utility. But system preferences was running and you could do anything with it. So the sensitive security preferences were working as they should, which is very surprising because those are very sensitive permissions that you can change there. By looking in Activity Monitor, it was clear why this was the case. So system preferences itself was now sandboxed, as you can see here, but it uses different services. In this case, these are XPC services, and some of those were sandboxed, but others weren't, because XPC services are launched separately from the application. They do not need to be sandboxed when launched by a sandboxed application. So as you can see here, the account profile preference pane was not sandboxed, but there were other parts that were sandboxed. So Apple used a similar technology here as the Open Panel to draw the contents of the system preferences window from a different service. So the security preference is running in a different process from the main system preferences application. But there are also older preference panes that you can install as a user. So these are bundles. There's a translation happening using a legacy loader application that can be used to load those bundles into the new XPC services type of preference pane. Now, this was an interesting trick, but there was really no security impact yet. But then I noticed something else. System preferences was creating a number of files within the container of this application, within the cache folder where application keeps its cache files. It was creating 3 files. One of those is the user cache file, which contained a list of the third-party preferences panes that the user had installed. So these are bundles, and it didn't verify the contents of this cache file, and it was located within the container of my application. So this meant that I could do the following. I would launch system preferences within my application container. I wait for it to create its cache file. I terminate the application, which is allowed because it is running within my own container. And then I modify the cache file to point it to a different bundle for a specific preference pane. I launch system preferences again. And then I wait for the user to click on the modified preference pane. What then happens is that a different bundle is being loaded in a non-sandboxed XPC service, which means that it is executing outside of a sandbox. We have a demonstration of this here. So first of all, to show that this is sandboxed. As you can see there, it is sandboxed. Launches system preferences, terminates it, and now it's launching it again. The user clicks on a preference pane and calculator starts. Now this is a sandbox escape, but it's not very interesting because it requires user interaction. The user needs to open that preference pane And the chances of the user doing that when you just spontaneously open system preferences is a bit low. So I looked for a way to open a specific preference pane. And first I looked at using a specific URI scheme. It's used to be supported, but it is no longer allowed for third-party preference pane. So you can load a specific preference pane from Apple, but not a third-party pane. But there is something new in preference panes, and that is the ability to add alerts. So what you've probably seen is this badge on system preferences. When there's an update waiting, you see this badge appearing because there's something that needs to be installed. Now, any preference pane can add this alert, even a third-party preference pane. And if you start system preferences the first time after a new alert has been added, then it will automatically open the preference pane that added this alert. So I could shorten the attack to this, create a new user cache file, add an alert for an injected preference pane, and then start system preferences. And this made the attack much faster. We have another recording of it, but you really need to pay attention to even see system preferences starting. It's first demonstrating again that it is sandboxed. And there's calculator to show that it is running in sandbox code. Apple fixed this also in the Big Sur update. Now system preferences automatically exits if it is within a sandbox, which makes sense because it's not expecting to ever be in a sandbox. Next up is Electron, and how TCC is often vulnerable when used on Electron applications. So as Dan mentioned, TCC permissions are stored based on two things, the bundle identifier of the application and the developer identifier. This means that the version of the application and the path on the file system are not relevant to the permissions it has. This means that if you download an upgrade, then that upgrade automatically still has the TCC permissions that you gave it. And also what Dan mentioned is that the code signing check only checks the executable itself. Now with a hardened runtime, this also means that the libraries and frameworks are being checked, but any interpreted code within the application is not checked automatically by Gatekeeper, only if an application is downloaded from the internet. And the Electron apps contain most of their code as JavaScript files. So there's this attack that works on all Electron applications. You copy the application to a writable location, if it's an application, so you cannot just change it. Replace JavaScript with some malicious JavaScript, launch the modified application, and now any TCC permissions that the user gave to that application are usable from your malicious JavaScript. And the code signing of macOS doesn't detect this. And as it happens, many of the Electron applications that you may have often require access to your camera or your microphone. So these are all applications that are written with Electron, and many users will have given webcam or microphone permissions to at least one of these. And as a user, there's really no good way to protect yourself against this, because you cannot temporarily give permission to your microphone or to your camera using TCC. The best thing you can do is monitor if your webcam is being used while you don't expect it to. For example, you can use oversight to see if your microphone is being used or your webcam is being used. And then you know that something is using it even though you don't expect it to. And the problem is even broader than just Electron in many applications, because library validation is relatively new. So for many applications, you can find an older copy which doesn't have library validation yet, and you can download that, replace any library, launch that modified application, and then you can use all of the TCC permissions of the application. Even though you're using an older version, it still has the permissions that the application has. This is really a vulnerability that an application itself cannot protect itself from. It's something that is a problem in the design of TCC, and Apple will need to find a solution for this. Finally, we're going to talk about process injection. As we mentioned before, process injection can be used to communicate with a privileged helper tool, for example, to install an update. But you can also use it to steal permissions, in the same way that you can modify an Electron application. If you can inject code into another application, then you can borrow the TCC permissions that application has. But one thing we found was we found two generic process injection techniques, and then we tried to find what is the impact of these, what is the full range of things that you can do using just a process injection vulnerability. So we looked at what can we do if we inject into Apple's own applications. Now, these vulnerabilities are still being worked on by Apple. They applied some mitigations, but they are still they still asked us to not disclose the full details. So we cannot give all details, but we can describe how, if you have this vulnerability, you can exploit it. So suppose you have a process injection vulnerability into any application. Then we found that you can escape a sandbox, you can escalate privileges from normal user to root, and you can bypass SIP file system restrictions. So any files that are protected by SIP, you can modify or read, even though that should not be allowed. First of all, sandbox escape is a bit boring. If you can inject into any non-sandbox process, then you have a sandbox escape, because then you're executing outside of your sandbox in a different application, which is a sandbox escape. And we cannot give more details than that for this specific vulnerability. Privilege escalation is more interesting. There are a number of applications that Apple includes which have an entitlement that looks like this. So they have a authorization services entitlement with an array, and that array can include a number of different things. One of those is installing Apple software or Apple software as a standard user. And where this is used is in, for example, Bootcamp, but also in install command line developer tools. This entitlement allows an application to install a new Apple signed package without the user entering their password. So these applications can install some new components that they may need for something. So we can install a new package, but it has to be signed by Apple. Now, luckily, we didn't have to look through all packages signed by Apple, because somebody else, Ilyas Morvat, found that the post-install script of a specific package, the macOS public beta access utility, can execute code as root if you install it. This is the other vulnerabilities in that blog post are now fixed, but because this package was signed and it still has a valid signature that Apple hasn't revoked, you can still install it to exploit this issue. How this works is that it tries to run a command relative to the disk that you install it on, but it doesn't check that the disk you install it on actually has macOS on it. So if you install to a new RAM disk or some other type of disk that doesn't have normal macOS files, then it will still try to run this command. So by creating this specific path, it is possible to execute a script as root by a application that has this entitlement. So by injecting into an application with the authorization entitlement to install Apple signed software, and then installing this package to a disk, it's possible to execute code as root. Finally, to bypass SIP file system restrictions, we found an application included in the macOS Big Sur beta disk image, which has a very powerful entitlement. This is the rootless install heritable. This means that it is exempt from any file system restrictions, and also that it is a heritable entitlement, which means any subprocess it starts also have this entitlement, which means that it can write to any location which is protected by zip, which it is not yet fully equal to kernel code execution, but you can use this to load a kernel extension as long as it is signed without user authorization. So if you want full kernel code execution, then you need to find a vulnerable kernel extension or something else. But it is pretty close to that. We have a demo video of all 3 vulnerabilities here. So first we demonstrate that this application is sandboxed, and then we go through all 3 steps. And then demonstrate that we have bypassed zip file system restrictions. So here you see this application was indeed sandboxed. We start a reverse shell. Now the privilege escalation step is running, which is a bit slower because it needs to do the installing of package. And then the zip, which is quite quickly. As you can see, this is now running as root. And to demonstrate that we have root access, we go to the system policy configuration directory, which is where your approved kernel extensions are stored. As you can see, we can create a new file there. So, some of our thoughts about these security measures. Do they actually work? First of all, TCC. TCC is still pretty new. It's not well known by developers. If you report a vulnerability related to TCC, then often you need to completely explain everything about it before they even realize that it is actually a vulnerability. And you only need one application to be vulnerable with a TCC permission to have malware that can also get that permission. There are many applications, Electron, but also all the older applications that did not have library validation, that are inherently vulnerable and that cannot be protected using the current code signing mechanism that macOS uses. Sandboxing. Now, sandboxing on macOS benefits a lot from the research on iOS. So there's a lot of active research on iOS for kernel vulnerabilities for jailbreaks, and those often also apply to macOS, which gives those parts a lot of attention. There's also higher level layers for sandboxing, like the open panel, and this appears to be completely unexplored attack surface, because something as simple as taking a snapshot from a different view is still here, and those types of vulnerabilities should be easy to spot if somebody looks at that. Finally, there might be some questions for you about how this is applied to Windows or Linux. I have to say, we know a lot less about those systems than we know about macOS, so take this with a grain of salt. But as far as we know, there's no security boundary between different processes running as the same user on Windows and Linux, unless you opt in to sandboxing, so UEP or SE Linux. Then there's a security boundary, but otherwise all applications can access all hardware features or all files that are accessible to that user. So TCC in that regard is a completely extra security layer that is not applicable to those systems at all. And if you break through TCC, then that doesn't make macOS less secure than Windows or Linux, because that layer is not there at all. However, there's another way of looking at it, that process injection on macOS is now a very big issue. If you have a generic process injection technique, then, as we have demonstrated, we can escape a sandbox, privilege escalate to root, and then even bypass zip. So, because the assumption is that process injection is not possible, there are many technologies or many parts of the system built on the assumption that it is not possible. While on Windows and Linux, the assumption is that process injection is just something that happens, which means that it's very difficult to compare those measures to Windows and Linux. Finally, conclusion. Apple is trying to bring the security of macOS to the level of iOS, but it still has a long way to go. There's a lot of work needed from application developers because stuff like this is not easy to implement. And existing applications, Apple doesn't want to break existing applications all the time. They slowly introduce new security measures, but they cannot enforce the same restrictions as on iOS in one go. So that's why the current measures are good, but they still require a lot of work.